So welcome everybody to this webinar on using the OpenMP tasking model and understanding OpenMP tasking. This webinar is brought to you by the POP project. It's an EU-funded Center of Excellence project. POP stands for Performance, Optimization and Productivity. So we in this project deal with a task to analyze and optimize the performance of applications. And we're talking about OpenMP tasking for two main reasons. First, we think tasking is really a very nice way to express parallelism, which deserves more attention than it is getting at the moment. And second, there are a couple of things that are crucial in order to get good performance from OpenMP tasking. And this is what we learned in our practical work. So in this webinar, in the next approximately 30 minutes, we would like to present OpenMP tasking, what it is, and what are the main features, and what are the crucial aspects that you have to take care of when you want to get performance from OpenMP task parallel programs. I'm saying we, so we are two speakers, and we try to make this interactive. So we prepared a little chat about OpenMP tasking. My name is Terboven.
Hello, my name is Dirk Schmidl. So very few organizational remarks. So you can ask questions during the webinar if you use the chat menu, which you see in front of you. So we might not see all the questions while we are presenting, but we will try to answer as many questions as possible at the end of the webinar. Also, if you ask a question during registration and you didn't receive an answer so far, we will also try to answer those questions if there's time.
Okay, so let's start. So Dirk, I heard about this OpenMP tasking. I attended a couple of conferences and read some books. So I learned OpenMP 3, which was released in 2008, introduced this concept of tasking. And I tried to understand what a task is, and I heard from some guy in a tutorial that task is actually a package of code and data. So it means it's something that can be executed independently from all the other tasks. Code means that actually the code being executed as part of the task, and data means that is the private data that's private to this task, but obviously a task can also own references to shared data. The interesting thing apparently is that tasks can be nested, so that means it's a very good way to parallelize recursive or in general irregular algorithms. Now in OpenMP there are also special constructs. For example, the task wait construct is a task-only synchronization construct, which makes encountering task or thread, meaning the task or thread that encounters the task wait construct, suspend until all the child tasks, the direct child tasks, have been completed. So that was my high-level overview. So there's this OpenMP task with a structured block. The structured block comprises the code, and the clauses are there to refine the data environment. So I set myself out to parallelize one of those really important problems in computer science, namely the computation of Fibonacci numbers. Okay, not kidding. I really wanted to understand how to parallelize such a recursive code with the additional challenge that in every recursion step there's only a very small amount of work to do. So I'm a C or C++ programmer. This is my implementation of Fibonacci. I know there are better ways to compute the Fibonacci numbers, but I'm more interested in parallelizing this recursive algorithm pattern, which I think is very suitable or very similar also to parallelizing a tree search and graph search and other approaches. So here I'm calling Fibonacci with a given input, and then I have my Fibonacci implementation. If the n is small enough, I'll just return it. Otherwise, I say x is Fibonacci of n minus 1, y is Fibonacci of n minus 2, and then I compute x plus y. Okay, so I set out being a brave programmer and parallelize this with OpenMP. I have a parallel region to give me a team of threads. I have a single construct, which means one thread will execute the body of the single, which is this first call to Fibonacci. The others will wait in the implied barrier. And then I have the, let me call it a left-hand branch and the right-hand branch. Yeah? And I have this OpenMP task wait, so that x and y are actually computed in the respective tasks, yeah, x and y, before the sum is computed and returned. I have to say shared x and shared y to prevent the compiler and runtime of giving me a new x and y for every task. Here, because I want to use the same x and y of this respective instance of within the recursion to be able to compute x and y at the end. Okay, yeah, so parallel, single, parallel to get a team of threads, single to have one thread starting the execution, 2 tasks, and the task wait. This was my idea to parallelize this code. How does it now work in practice? So that's still a little bit unclear to me.
Okay, yeah, Christian, it was a good approach, and let's see how this really is handled by the OpenMP runtime if you parallelize such a recursive code. So I'll try to illustrate this here. So in the OpenMP runtime, you have something which is called the task queue, and as you mentioned, a task is a piece of code and some data which is packed together and which can be executed by some thread of OpenMP. So here I try to illustrate, we have a program or parallel region with 4 threads, so T0 to T3. And in your code, there was a single region, so one of the threads will start executing the single. Let's assume this is T0 here. And then in the single region, it will call Fib4, for example, if 4 was the input to start with. And yeah, the other threads just skip the single region and are waiting in a barrier. So at the moment, they are not working at all. So, and then the thread 0 will call Fib4, and inside of this, you had 2 task pragmas, one to compute n-1 and one n-2, so Fib of 3 and Fib of 2. Your OpenMP program will create 2 tasks and put them into the task queue, as illustrated here. Now you have a task queue with 2 tasks in it, and yeah, you have threads which are waiting in the barrier. So what can happen now is that these tasks are taken out of the task queue by any of these threads. Of course, instead of idling in a barrier, it's more useful if there is real code to execute, which are the tasks here, to really compute some useful results. So after one level in your recursion, now you have thread 0 and thread 1 both executing a thread, and you have really parallel work here. And then you continue. On the next recursion level, both of them create 2 tasks, so in total you have 4 tasks now in your task queue, and every thread can now pick one of the tasks out of the task queue. And on the second recursion level, you get 4-way parallel, so all threads are now executing some useful code, so some of your tasks. And you can imagine if you start on a higher recursion level, you can utilize a lot of threads that way, also if you just only create 2 tasks on every recursion level. So this is how basically the task execution works in your example.
Okay, got that. Thank you very much. So let me come back to my code. Yeah, if we remember that this is the performance I got. So what I'm showing here is my first approach. Yeah, it was 3 slides ago, over 1, 2, 4, and 8 threads. And I would really like to have seen the blue line, which is the optimal or linear speedup. But what I got is this lousy grayish line. So with 2 threads, I got a speedup of 2. I was feeling really good when I saw that, but with 4 thread, I got a speed up of, let's say, 2.7, and with 8 thread, I was even below 2 again in terms of speed up. So this is when I stopped continuing with my experiments here. So you said this works like magic, but I'm missing the magic here. What's wrong?
Okay, so let me explain a bit more what's the problem here. So to get an understanding of what's going on, we always recommend using some tools to give you some insights in the performance of your program. And I did some performance analysis of this first version you parallelized with Fibonacci with performance tools.
Oh, you're well prepared. Thank you.
Thanks. So what you can see here on the left-hand side of the slide are basically 2 screenshots of the cube GUI I did some performance measurements of the application, and here what you can see is how many tasks were executed overall and how much time was spent overall. So you can see that there is more than 4 million tasks. Sorry, there's threads on the slides, it's a typo. So more than 4 million tasks which are executed, and overall in CPU time of 10.8 seconds roughly. So if you compute the average duration of a task, it is 2.6 microseconds, so which is very small work to do. And yeah, of course there is some overhead involved with the creation of a task. You queue it, you dequeue it, you have some synchronization between the threads. So yeah, this is quite small tasks. If you have a closer look at it with a tracing-based performance tool like the Vampire tool I show on the right-hand side of the slides here, what you can see here is basically the call stack of the master thread when it executes this program. And what I want to point out here is on the different levels in your recursion, the tasks have a very different size. So at the upper levels, like on level 13 shown here, you have tasks of the duration of 0.1 second roughly. So this is a pretty big task. If you go down the recursion, yeah, as you can imagine, the calls to Fib get a smaller and smaller input. So you have less and less work to do on the lower levels. The tasks get much smaller. So on level 34, you are at 1.7 microseconds. And on level 66, which is pretty down in the recursion, you end up with very, very tiny tasks. So it's less than 1.5 microsecond. And yeah, the reason that this does not scale is just the overhead, as I mentioned. To put a task into the queue, to take it out of the queue, is much longer than the real benefit you gain. And you can also imagine if you have 4 million tasks overall, this is much more than you need to really run in parallel on 4 or 8 threads. Yeah, so in the illustration you've seen that up at the second level you were able to utilize 4 threads. On the third level you were able to utilize 8 threads. And then if you create 500,000 tasks on every thread, this is creating a lot of overhead, but you don't need any more parallelism since you don't have more threads to pick up those tasks. So what you can do in OpenMP to reduce the overhead is you can use an if clause together with the task pragma. And this can help you to basically not create the very fine-grained tasks. So you can, in your code, add an if clause, and only if this if clause evaluates to true, the task is created. Otherwise, the task is immediately executed. So this means the if clause still needs to be evaluated. You still need to create a data environment, but you do not put the task into the queue and you don't take it out of the queue. This reduces the overhead a lot. Okay, so if you do this in your Fibonacci example, like shown here. So let's stop creating tasks at a level of n equals 30, and then just not create the very tiny tasks at the end of the Fibonacci calculation. And then you can reduce the overhead, of course. And if you look at the performance you get with these simple changes, now you see the scaling is much better. So now you're still not at the optimal speed up, but you can see even after 2 threads, with 4 and 8 threads, you get significant speed up, and you come at least to a speed up of close to 7 with 8 threads. Yeah, the reason why you're still not at the optimal speed up is this if clause still needs to be evaluated for every task down in the recursion. So you still have to evaluate 4 million times this if clause, and this of course still adds some overhead to your program. If you want to get rid of this as well, you can also write a separate function, which here is called zerfib, which is the serial version of this function you've shown at the very beginning. So without any OpenMP pragmas. And if you reach, in this case, the n equals 30, you just call this version once, and inside of this version, you have recursive calls to zerfib again, which means you will never reach an OpenMP pragma again. You will not evaluate the if clause again, and this will reduce the overhead even further. But yeah, then you can get a better speed up as shown here. So the black line is a third version, and this is really now on the optimal line which you calculated. So now you get a linear speed ups and everything scales fine with OpenMP Task, and you can utilize all your threads, but you don't create that much overhead that you really get the lousy performance you've seen at the beginning.
Oh, so you're calling my version lousy, huh? Thank you very much. No, thanks for the explanation, Dirk. So let me try to summarize that in my own words. So the tasks are all independent from all the other tasks, and as we have seen here in the source code examples, tasks can be nested. So we only have one parallel region, which gives us a team of threads, and then we use this single construct so that we can implement a single worker approach, meaning only one thread or task, depending on how you want to call it, starts the execution of Fibonacci with the input value. And then this initial task is creating more tasks, which then are creating more tasks, and so on. And on every recursion level, we have the task wait to wait so that we can actually compute x plus y. And you very nicely illustrated how the OpenMP runtime is mapping tasks to threads. And what I learned from you is that the OpenMP runtime is very efficient in mapping thousands or even millions of threads to tasks. But although being efficient, there's a certain overhead involved in every operation. So that means we have seen it here. If the tasks become too small, they might not pay off or pay back for the overhead. So that means at some point in the recursion level, we have to implement what computer science calls a cutoff strategy, so that we have created basically enough tasks to keep all the cores and threads busy, and not too many tasks so that the overhead still remains within a manageable scope. Good, I think I got that. And for the others, also new to tasks, there are many other things that are interested in tasking. I just selected 3 different topics which I would like to present here. So I said tasks can be nested, and this is OpenMP's approach to support interoperable and more importantly composable code. So if you think of this loop here, A equals A of I times B of I times S, that's a vector multiplication or matrix multiplication or whatever. If you want to execute this in parallel with tasks, you first have to block it, so that a couple of iterations are grouped together. You always want to do that in order to get good performance from cache-based systems. So if you think of linear algebra codes or any linear algebra library, this is what will be done to some or even greater extent than shown on this slide below. So we have an inner loop, a blocked loop, which allows us to exploit the caches, so that later on all these blocks can be executed by different tasks. So before OpenMP 4 and 4.5, which are the current released versions of OpenMP, this was the tasking approach to execute such a loop, which is really ugly. So what OpenMP tried to support is that the user doesn't have to write this manual transformation on its own. And that was always tricky because one single iteration within a block is too fine. We have too much overhead, as Dirk illustrated earlier on. If we put the whole loop within a task, we can't exploit any parallelism. So OpenMP introduced the so-called task loop approach, or task loop construct, sorry, that's the right word. So we still need a parallel region behind it, to have a team of threads, but the task loop partitions a loop into a set of tasks which can then be executed by the teams within the parallel region. So it's not a work sharing construct. That's different from Pragma OMP4. This is not distributing iterations to threads. The task loop is partitioning a loop into tasks, and the grain size can be used for exactly that blocking which I tried to illustrate earlier. So it's the number of TS tasks that are grouped together, the number of TS iterations that are grouped together to form an individual task. So when OpenMP is saying we want to support composable parallelism, we are thinking of giving the programmer the ability to express more and more parallelism of his or her code with tasks. And the task loop could be a replacement for traditional loop-style thread-centric parallelism. Something what was missing and still is in current implementations is support for task reduction. So this will be introduced with OpenMP 5. It's already part of the current technical report, and that means it's part of some beta releases of compilers. So I assume you're all aware of reductions. That basically means if we want to perform a reduction on a variable, during the course of the computation, every thread or task will have its very own private instance of this variable, and at the end, all these private instances are reduced together to form the final result using the reduction operation, which has also been specified. That's in OpenMP for years and years on the for work sharing construct, but it's not there yet for tasks. So to support it in OpenMP, we have the task group, which is, was initially a way to support task synchronization, and it still is, but now we can also specify that this is the scope of a set of tasks to be used within a reduction. So all the tasks created within the dynamic extent of the task group, meaning all the code that's executed within the structured block at runtime, can execute in the task reduction. So this is the operation, for example, in addition. This is a list of variables which should be handled as reduction variables. And then on every task, we have the in reduction clause, again the operation and the list of variables. So let's take a look at an example here. We have the parallel single pattern again. A task group, we execute a while loop, which is almost impossible to parallelize with traditional for work sharing. Here we are creating one task per loop iteration. As long as the condition holds, a new task is created. And here we're using the in reduction clause. So all the variables res are made private per task, and at the end the global sum is computed because here the sum is specified as a reduction operation. And well, the final thing that I wanted to talk about today are task dependencies. So far in this webinar we learned about the task weight construct, which supports the synchronization or the weighting of the encountering task for all its direct child tasks, but not for all the tasks that are available, only the direct childs. Any children of these childs can execute past, can still be available within the task queue. So this was the kind of synchronization that we had in OpenMP 3.1. So if we had a task that prints X and then another task that increments X or modifies X, if we want to have a synchronization in between the two tasks, we had to specify a task weight. But the task weight would also apply to any other tasks created on this level here. So the new way of doing that in OpenMP 4 is to specify the data dependency. We call that, sometimes called a data flow between the tasks. So here we have this task which prints X. Here's the other task that increments X. And we say they both have dependency. The one has a dependency on X, so it's reading X. And the other has a reading and writing in out dependency on X. So that means it's modifying X. And that basically specifies that this task is created, because this task is created after the first one, this one has to wait until the first one is completed, because it would modify X, which this one is reading. So this is why I meant the dependencies capture the data flow. Yeah, so in OpenMP 3.1 we had a strong synchronization construct named the task weight, In OpenMP4, we can specify dependencies in between individual tasks. And many linear algebra stuff are good examples in the literature for applications needing this kind of fine-grained synchronization control. Yeah? So we're trying to get rid of all the hard barriers and or task-related barriers. And we are trying to express or enable the programmer to express the fine-grained granular dependencies between tasks so that the runtime can optimize the execution of the task to exploit the maximum amount of parallelism. So this is what we have been, what we have prepared for today. Now we try to give you an overview about the OpenMP tasking model. So we started with a brief overview of how a tasking runtime might work under the hood. We explained how tasks can be used to parallelize recursive algorithms. And at the end, we gave an overview about task dependencies, task reductions, and something else which I just forgot. Sorry for that. And the task loop construct, which is a syntactic sugar for the programmer if he or she wants to parallelize loops with OpenMP tasks. I hope this was useful. Thank you very much for your attention. And I guess we have some questions here. Is that right, Dirk?
Yes, that's right. So the first two questions we have are the question which profiler was used for the performance analysis here. So I used for the performance measurement the SCORP measurement system, and for visualization on the left side it's a Cube GUI, which is part of the Scalaska toolset, and on the right hand side this is a Vampire trace visualizer. If you like to get some more information on the POP website, which was shown here in the section about training material, there is an overview of all these tools, or some links where you can find the tools for download and where you can find further documentation. So if you like to use them for tasking programs, this should work as well and should be documented there.
Good, I can pick up the next question. So the question was, unfortunately, the programmer is bound to use Visual Studio, and he realized that Microsoft is only supporting version OpenMP 2 or 2.5, which was released before tasking came to existence. So the question is, do I know why they do so? I'm probably not allowed to tell. My personal opinion is they don't care about OpenMP anymore. They also left the OpenMP Architecture Review Board. And the other part of the question is there any support to overcome this restriction? I think so, yes. So first, there's the Intel and the PGI compilers available for Windows with integration into Visual Studio. Obviously, they are also commercial compilers, but they bring better OpenMP support, including the Intel compiler doing full OpenMP 4.5 and 5 beta support, if you like. But there's also an open source, or let's say end cost-free alternative, which is a Clang compiler. So Microsoft is improving its support for open source software in general. So that's my personal opinion. And they made Clang a full-featured compiler, or fully supported compiler within their Visual Studio environment. That holds true for Visual Studio Code, the free part of Visual Studio, and all the paid variants of Visual Studio. So you can make use of Clang, which comes with the same OpenMP runtime as the Intel compiler, at least conceptually, and with respect to the main features. And that means you have full support for OpenMP on Windows, at least from a development point of view. Whether that's excellent support for a shipping product, I'm not an expert to judge on, but this is then where you have alternatives like Intel or PGI.
Okay, so I can maybe answer the question about nested tasks. So the question was, are nested tasks always executed by the same thread? So this is not the case. So as I tried to illustrate here, in the Fibonacci example, you basically start with this Fib4. So there is one task which is executed by thread 0. And the nested tasks of this task are Fib3 and Fib2, and they are executed by thread 0 and thread 1. So also thread 1 can pick up a child task, and on the next level, all the child tasks can be executed by all 4 threads. So whenever you put a task into the task queue, any thread of the current thread team can pick it up from the task queue and execute it. So there is no limitation that it must be nested tasks. This would also limit the usability, because it would be harder to express parallelism or to get work balancing with tasks. So this is one of the advantages. Another question was, again, which trace analyzer was used. So this was Vampire as a name. So
good. So there's a question: how is a task loop an improvement over parallel for? Let me go to that particular slide here. Okay. So if you have a single loop, yeah, with a set of iterations, and you know the number of iterations, and you know they are all have the same cost, meaning computational expense, and you want to have a static access pattern, then there's nothing wrong with parallel for, and actually it will give you the best performance. So if you want to map iterations to threads and have full control over these threads, the parallel for is a way to go. However, if you're having to nest multiple loops, yeah, and for example, at the time of the writing of the program, you don't know how many loop nests will be executed, what's the length of every loop at each level, what's the computational cost of individual iterations, yeah, possibly there are load imbalances in between iterations at a certain level or in between different levels, then a parallel for is not the right thing to go for. If you want, you can add the parallel for with a dynamic schedule, but that doesn't help if you want to nest multiple loops into together, because then you have trouble with the thread management. So it means if you need composable parallelism, tasking is a better approach, because it adds in a layer in between, let's say, the expression of the parallelism and the mapping of the parallelism to the runtime, or basically, sorry, that is the level or the layer that tasking is adding. Yeah, so you're not deciding how to distribute iterations, yeah, which is something that you have to specify at compile time. If you're using tasking, you're expressing the parallelism, and the runtime it can exploit that in together for also with other tasks from different software components. You can specify dependencies and so on. Just to name a few examples. So the runtime can exploit this knowledge to map the tasks to the available threads. So it gives you an approach to handle composable or to introduce parallelism in a software that's composed of multiple components. Yeah, so if you have a static loop and you're happy with that, no reason to switch to tasks. If you're dealing with load imbalances, multiple loops, and situations which I've just described, yeah, for example, if you have logs in to make sure that different iterations within a single loop don't modify the same amount of data. In many cases, we have seen that task loop plus dependencies can lead to a better performance, because the runtime has more details to exploit and optimize the mapping of tasks to threads. I hope that answers the question.
Okay, so we had another question, so that is more. Yeah, so you realized that the algorithm is not optimal to compute Fibonacci numbers. Yeah. So the question is, we compute Fib of 2, for example, 2 times by different threads, and this is not a good thing to do. Yeah, you can have a different algorithm which doesn't use the recursive approach and doesn't recompute some of the values, and this is true. We just chose it because it easily fits on a slide, and it's a very simple recursive description of a problem. If you rewrite it iteratively, not to recompute anything, and you just store 2 values basically, then you get a much faster algorithm for it. But for other algorithms which are of recursive nature, you can use tasks in a similar way. And we just chose this very simple algorithm for illustration purposes because it easily fits on a slide. But for example, if you think of a tree search, then it's not that easy to come up with an iterative approach, and you don't recompute things there. So that,
so the question is, what's the status of OpenMP version 4, and I extended to 4 and 4.5 in various compilers. So OpenMP 4 and 4.5 are the versions that are released, and I guess most compilers, except for Microsoft Visual Studio compilers, support currently OpenMP 4 and 4.5. Yeah, maybe there are also some limitations on PGI. So what I'm basically saying is that Clang, the Intel compiler, the IBM compilers, and GCC do also support all the features of OpenMP 4 and 4.5. OpenMP 4 also introduced support for heterogeneous programming, like including GPUs for acceleration, or coprocessors like Xeon Phi, or FPGAs or whatever. But this is always depending on your target compiler and target architecture. So Intel obviously doesn't support NVIDIA GPUs, but Clang and GCC do. However, Clang is better on, for example, Open Power architecture in supporting the GPU than it is on x86-based architectures, but it also works. Implementations on that are still kind of young. Yeah, so if you think about how many people are working on such a compiler, to implement features like OpenMP Tasking takes a couple of main years. It also takes a couple of years for the GPU support to mature. So if you want to support, if you program, there's just another question arriving. If you want to program for GPUs in OpenMP, the best implementations are Clang and IBM's compiler on Open Power. There's a Cray compiler on only Cray architectures. On x86, you also can deal with Clang and GPU and GCC. Also, performance is limited. Intel only support their own integrated GPUs, which, as far as I know, don't give you too good performance. NVIDIA PGI have announced at this year's SC that they will support architectures or GPU architectures on x86 with their future compiler releases at some point next year. So on the Microsoft side, I said that there's no, I don't see any movement in the Visual Studio compiler to improve OpenMP support, but they support Intel and PGI compilers on Windows as well as open source Clang compilers. So I guess that's in the way to parallelize or compile certain components that require a state-of-the-art OpenMP parallelism.
Okay, so we have one more question, which is if the performance varies with different architectures like x86 and ARM. I think this is hard to answer. So in general, the performance of a program will vary on a different architecture, and this is also true for task parallel programs. So the concept of tasks should be, of course, architecture independent, and the idea is that you can write programs which should be performance portable, but this is of course always a goal which is hard to achieve, but there is no reason why tasks should perform better or worse on one of these architectures. Of course, the OpenMP standard specifies what tasks should do, then there's the implementation. You can have a better or worse implementation, and not all implementations are available on all architectures. So yeah, it really depends on many things, but in general, tasking should be a good way to express parallelism independent of the architecture. But I would expect performance differences if you go from one architecture to another for various reasons, not only for tasking.
And there's something like the standard OpenMP implementation coming into existence. So Intel many years ago open sourced their OpenMP implementation, which is now officially the LLVM OpenMP implementation, supported obviously by Clang and Intel, but also on Open Power architectures by IBM, yeah, and in the future possibly also by GNU. There's already flag so that the GNU compiler can be made to target, or can be made to work together with a LLVM OpenMP runtime. So that means, and this runtime is available on x86, on OpenPower, and on ARM. So performance should be good on all the architecture. Can we mention a good reference for task parallel programming? Yeah, maybe. So there's the book available from Ruud van der Post called Using OpenMP. And a couple of weeks ago, the new book was released. It's called Using OpenMP, the Next Step. So be careful. I happen to be one of the co-authors. So the book was written by Ruud van der Post, Eric Stotzer, and myself. And we have a chapter on tasking. So it's a lengthy chapter explaining all the details. And we tried to really cover, at least briefly, every aspect of tasking. And we will explain concepts like the cutoff with its performance implications that we looked at today. Yeah, using OpenMP, the next step from MIT Press.
Okay, then next question. Is thread binding beneficial for OpenMP tasks? So in general, thread binding, in my opinion, is a good thing to do. Of course, you don't benefit if the operating system decides to migrate your threads around while your program is executed in nearly all cases. So if you activate thread binding when you start the parallel region, the threads will be pinned. You still have the flexibility of load balancing from the tasks. So this is still working very well. And yeah, you can get some performance benefits, but yeah, it always depends on what your program does. But in general, I would recommend to also activate thread binding if you want to have the best performance. Okay.
I guess we mentioned, we answered all the questions. Yeah, there was one question from registration. So the question was, in task dependencies, do we support the overlap of array slices? So what I didn't mention here is you can specify in out x, yeah, but you can also specify in out x and then provide, given that x is a pointer or in general of array type, you can specify a certain slice, meaning a subset or subslice of the whole array. And if you have two tasks with overlapping slices, that means there's a dependence. If you have two tasks pointing, both being dependent on x, but with different slices, that means there's no dependence. Yeah. So I guess the question was: is there any plan to include in OpenMP task dependencies of data regions that intersect? Yeah. So if I understand the question in the way which I just explained it, I guess it's already there. Okay, so taking a look at the time now, I guess we will answer the other questions that might come in later or from the registration by email. John, is that okay?
Yes, that's fine. Yes.
Okay. Good. Is there anything else? Okay.
I think we are done. So thank you very much for your attention.
Yeah, thank you. And these were good questions. I like the discussion. Have a nice day. Bye-bye.
Bye.